Good morning, everybody, and welcome to this presentation today. We will be talking about FME for precision farming. I'm Ariel. I'm an engineer working as GIS specialist at Genesis GI, which is a company specialized in geospatial application. And Genesis is also a Safe Software Gold partner. I work also as JS consultant at Topcon Agriculture. Here's the agenda today. So we will start with some concepts on precision farming. Then I will introduce you the Topcon Agriculture platform and what's the challenge of this project. A data streaming on the cloud in real time. I will describe the solution we proposed based on FME and the results and benefits we obtained. In the end, we will have some time for question and answer. So what is precision farming? We can consider it as a management concept based on observing, measuring, analyzing data in order to define a decision support system able to optimize the line of actions for farmers in order to preserve resources. To do that, we need technology. So sensors, devices, self-drive vehicles with GNSS systems, all of them collecting data in an integrated way in what we call a smart farm. In this scenario, Topcon Agriculture is one of the biggest players in terms of technology solutions for smart farms. They provide hardware like specific sensors, consoles, GNSS integrated system for automated guidance, and so on. Topcon also provides a software solution. We said we need devices recording data, but the key value is the ability to process, analyze, and visualize properly the data collected on the field. And here comes the Topcon solution, TAP, a cloud-based platform for data integration in real time and maps visualization. TAP is designed specifically for companies and farmers who want to manage their field in a smart way. We think the best way to visualize data are maps. And we want good maps, but to have good maps, we need good data. Since the data are collected with sensors in the field, they can be affected by errors, like any kind of field monitoring practice. So we need to manipulate them and properly clean them. The challenge of TAP is to optimize the automatic data streaming from sensors, and they can be any kind of sensor from multiple brands, to maps, which will be the final support system to take decision. The proof of concept we put in place in this project is a process that goes from unstructured source data to a structured database for normalized data in order to publish maps. The solution proposed is based on FME, of course, transforming data from an alphanumeric, not easy to read source to a clean and clear map as results. Now, let's get a bit more in details on the architecture of our solution. The source point is a MongoDB database, which is a document-oriented database classified as NoSQL, which uses JSON-like documents with no predefined schema, no structure. And the Atlas source is a cloud-hosted service on Azure. This is where are stored all the sensor raw information after being uploaded by consoles or directly by farmers. From here, we want to move to our destination environment, a structured Postgres with Postgres as spatial extension database for vector data, associated to Microsoft Azure Cloud Storage for rasters. All of these layers will then be published on the web via GeoServer. The solution proposed is a FME workspace run on FME server with automation. Specifically, the design, the development, the deploy is done in FME desktop environment, including the uploading on the server side. Here, the workspace is triggered through an HTTP call from the TAP backend. The server environment is also configured with FME automation with topics in order to track all the events of the jobs. Here, a synthesis of the workflow, which is divided in 4 main steps. The start point is the reading and extraction of sensor data from MongoDB. Then we have the processing part. Firstly, the vector generation, representing the footprint of sensor and vehicle passes. Then the generation of raster layers to spatialize the data across the entire field. And in the end, the results are uploaded on the cloud to be published. Now, let's see some key points of our workspace. The data extraction is managed by the MongoDB readers, which support the Atlas Cloud connection and allow the customization of requests via JSON queries, so that we can read only the data we actually need. Then we have few JSON transformers, like the JSON fragmenter, list exploder, JSON flattener, that are very useful to navigate a complex JSON document and expose its information in a structured table. Let's keep in mind that in our case, every agricultural operation on the field is stored into the cloud as a task document associated to a point-by-point collection of sensor data. Once we have extracted all the data of our interest, we want to clean them. And here we design a sequence of transformers for statistical filtering. Statistic calculator, tester, test filter, no-filter tester, all of them combined together in order to remove the outliers, remove invalid record points, noise, and all the bad data associated to a field task. Once we have our valid sample of data, we generate vectors, starting from our point-by-point information in order to define the passes of footprints. Here, we use a sequence of the following transformers: offsetter, rotator, line builder, coordinate extractor, line closer. And using the GPS location associated to our spatial point and knowing the engaged implement section and its orientation along the path, we can build the vector polygon for each position in the field. Then we want to generate raster layer in order to spatialize our point-by-point information along the entire field. Here, we use an external open source geospatial library, Wildbox tools, which give us access to a large number of interpolation algorithms and statistical filtering. This library is based on Python, and thanks to the Python caller, we are able to increase the capabilities of FME with additional algorithms, all in a single workflow. This means that we can always call something external from inside our FME workspace without actually change environment. In the end, the results obtained are uploaded on the cloud infrastructure. We use the Postgres and PostGIS writer to upload the vector layers along with all the alphanumeric information. And we use the Azure File Storage Connector Transformer to upload the raster layers on the Azure storage. On the cloud side, we have the FME server, which automates the cloud data stream in real time. As a matter of fact, the workspace is triggered through an HTTP call. Moreover, the FME automation allows us to keep track of all the success and failure events related to every job. In this way, FME server is able to communicate with the entire platform backend within an integrated system. And here we are. The results of the full process are our amazing maps published in TAP. These will be available for the farmers for further analysis and decision making. So as we saw, the configuration we designed offers the benefits of an integrated cloud platform solution, leveraging the capabilities of connect, transform, automate data stream in real time. The successful keys of FME are the quick development, it's easy to deploy, and thanks to all the tools provided by FME, it's easy to control and maintain the entire system. Thank you very much for your attention. Here is my email. Please feel free to get in touch with me for any question and any doubt. And I hope to see all of you in the QA Zoom room that will happen right next the end of our presentation. Thank you very much.